Okay, so to start with, what we're going to do is we're going to deal with your definitions of your sides of your triangle, because this is important. Now, whenever we deal with these definitions, it matters where your angle is. These definitions come from your angle. If your angle moves, the definitions of your sides move. The only side that does not matter on where your angle is your hypotenuse. Which side is your hypotenuse? Yeah, the long one, the one across from your right angle. The one that does not touch your right angle. However you've had it defined to you in the past. I should have just, let me just stop there because I'm not good at spelling. I already left out the O. I know. No, I left out the O in between the P and the T. So since I already failed at spelling, I'm just going to give up on spelling already. All right, so let me put my angle down here, and we're going to define it based on there. All right, so our two sides are our opposite side and our adjacent side. So opposite side is the side that does not touch that angle. It's on the opposite side of the triangle from that angle. So this side would be our opposite side. And then adjacent in geometry, adjacent always means touching. So we have two sides that create this angle, two sides that are touching it. One of them is already defined. It's already called the hypotenuse. So the other one we define as adjacent. So if I would move that angle up to the top, then my opposite and my adjacent sides would switch. So this is, for some reason, this is one of the hardest things in geometry classes whenever I teach them for students to grasp onto. Usually in this class it's not as big of a deal, but all right, so our 6 trig functions. So this is going to start your memorization. Unfortunately, this semester is very big with memorization. All right, so we're going to start with sine. Sine is defined as opposite over hypotenuse. Cosine is defined as adjacent over hypotenuse. And tangent is defined as opposite over adjacent. So those are the 3 you should have had in geometry. Those are the 3 that, they give you stupid little rhymes to learn, like SOHCAHTOA. Or old hippies are high on acid. You never heard that one? Yeah. You have to know the order, sine, cosine, tangent, but old hippies are high on acid. Hey, I don't know what your teachers are teaching. I've heard that one before. Okay, the 3 new ones. Yep. Cosecant, they're the reciprocals of these. Cosecant is hypotenuse over opposite. Secant is hypotenuse over adjacent. And cotangent is adjacent over opposite. So that's your first bit of memorization. Okay, next thing that we're going to be using a lot this semester, which hopefully you don't have to memorize, is Pythagorean theorem. Just wanted to review it real quick. We're going to use it in the next couple problems. A squared plus b squared equals c squared. Your opposite side squared plus your adjacent side squared equals your hypotenuse squared. Okay, again, just threw that in there. I don't know why. Make you feel better. Make you feel like you, oh, I got this. All right, am I good? Okay to switch? No? Okay. All right, let's do a couple examples. Just start off basically. All right, normally you're only going to be given two sides, so you have to find the third side, which is where Pythagorean theorem comes in. So I'm missing my opposite side, so to find it, so I'd have x squared equals 256 minus 49. Oh, I should have tried to do math this early. (207), which I'm pretty sure doesn't have a square root. So I'm just going to leave it as square root of 207. Nope. Since we're dealing with triangles, we can't have a negative side. So yes, technically, since I did a square root, it would have plus or minus, but negative doesn't make sense. All right, so sine would be opposite over hypotenuse. So it'd be square root of 207 over 16. Cosine would be adjacent over hypotenuse, so it'd be 7/16. Tangent would be opposite over adjacent. Cosecant would be hypotenuse over opposite, or you can just think of it as a reciprocal of sine. That would be a good, it's a good to start making that connection. Yeah. Yes. Yes. That's what we're looking at. I meant to write that in there.
Do we need to like simplify it if it's on the top?
No. Yes, CSC is the reciprocal of sine. Now, I don't think 207 could be reduced at all, could it? It could be what? 3 radical.
Yeah.
Okay, 3 radical what? 23? Okay, I'm sorry. So yes, we should have reduced it. Okay, so it's, you can either go ahead and just do, hypotenuse over opposites, but again, it's good for later on to go ahead and start making the connection that these are reciprocals of each other. So go ahead and we could just take this answer and flip it over. Now, I want to simplify that. Let's see, 3 times 23 is 69. Are you guys okay with that simplification, or do you want me to go through it?
Would multiplying by radical 23 on the top and the bottom, every just cancel out the radical 23?
Yes, but you're left with a 23.
Oh, yeah.
So yeah, so that's what I did. I took 16 over 3 radical 23, and I multiply by radical 23. So on the top, I just get 16 radical 23. Sorry, I'm running out of room there. On the bottom, it cancels out that square root, so I get 3 times 23. Now, a shortcut to that, once you get used to doing it, a shortcut to it is you just move this to the top and leave a 23 on the bottom. And that works all the time. Okay, so secant is the reciprocal of cosine. So this would just be 16/7. Cotangent would be the reciprocal of tangent. So that'd be 16 over 3 radical 23. So that'd be oh, I messed that up, sorry. Whenever I was rewriting, that should be a 7. So it should be 7 over 3 radical 23. So I move the radical 23 up to the top, leave a 23 on the bottom, which should be 69 again. Okay, so let's make it a little bit harder. I made this one harder, not so much in the trig, but with the Pythagorean theorem. What's my missing side? And you start writing bigger. You can't solve it because of the plus sign. Yep. That's the missing side. So whenever I put this in Pythagorean theorem, I have opposite side squared plus adjacent side squared equals hypotenuse squared, so I have x squared plus 4 equals h squared. Can't do anything to simplify that, so I just need to square root it. So that's my hypotenuse. This side is x. I can't do anything with that x. You were given that side as x. So what I have to do is this side is just going to be in terms of x also. So I just do what I can with it in Pythagorean theorem. So I get x squared plus 4. And then square root it. Now, if you have stuff like this, I am not going to force you to simplify your square roots with this because that will end up being a mess. Only time I'm asking you to simplify your square roots is if you have numbers. So, what would sine be? X over. Okay, what would cosine be? So see, the real difficulty with this was just doing the Pythagorean theorem. Once you have your sides, you just have to use your definition of your trig to put them in the right places. So tangent is still just opposite over adjacent. So tangent is just going to be x over 2. Cosecant is hypotenuse over opposite. Secant, hypotenuse over adjacent. Cotangent, adjacent over opposite. And again, notice each of these are reciprocals of each other. Yeah.
Could you do like a chart thing with a cross, like so that you just go across the reciprocals, like?
You can do whatever you want to wherever you're writing it. I intentionally didn't write it that way. Yeah.
Wouldn't we simplify?
Nope, you can't because of the plus sign. In order to be a perfect square, so that it would simplify, remember whenever you're dealing polynomials, a perfect square, in order to cancel out, would actually be this. That would be a perfect square that with the square root could cancel out. So x plus 4 couldn't do that.
But like, should we move it down to the bottom? Like not to the least square roots on the, in the numerator?
No, you're not supposed to leave square roots in the denominator. But I'm not going to, with the polynomials, I'm not going to make you simplify them. No, square roots can be in the numerator. That's fine. They're supposed to be in the numerator. They can't be in the denominator. Okay, now, all that was well and good. Those were actually the easier problems. This is what your problems are going to look like. You're not going to get a triangle. And I actually simplified this a little bit. You're going to be given this and asked to find the rest of your trig functions. So you're going to be given sine theta equals 4/9. What's the rest of your trig functions? Well, your first step. Your first step is just draw a triangle. This is sine. So what's my hypotenuse? 9. Okay, decide where you want your angle. It really doesn't matter where you put your angle. Decide where you want your angle. So if I put my angle down here, which side is 4? The left or the bottom? The left. So now I have the same problems that we have been having. You have to start a step behind. You have to create your own triangle from what they gave you. So now you do your problem and you get your bottom here. So let's see, 4 squared plus x squared equals 9 squared. So x squared equals 81 minus 16. So let's see, that's 71 minus 6, so that's 65. See, 65 is 13 times 5, so that's not going to have any way of reducing. Now, just to save us time, I just asked for cosine. So cosine of theta is going to be adjacent over hypotenuse. So there's my answer. So that's what your problems are going to look like. So they're just going to start you off like that, so you have to create your own triangle. Because in geometry, you were already given the triangles, so we have to move beyond that. Can't do geometry again. Okay, good with that?
Yep.
Awesome. Special right triangles. Okay, what are your two types of special right triangles? Do you remember?
30.
Okay, 30, 60, 90, 45, 45, 90. Okay, start with, let's do 45, 45 first. That one's the easy one. If you have two angles that are equal, that means the sides opposite them are equal, right? So that means these two sides have to be equal. Now, I don't know what letters you guys used in your other classes. Every teacher changes up the letters. I tried to avoid X's because X's are usually used in problems. A lot of teachers try to use S's because that's what the books use, but my S's look like 5, so I avoid S's. So I usually use N's. Okay, so if this side is in and this side is in, you remember what this side's supposed to be? N square root of 2. If you have any doubt about that, the way you prove it is you use Pythagorean theorem. So the whole point of this is it doesn't matter what size the triangle is, that relationship always holds true. So if this side here was 6, then this side also has to be 6. And this side, if you use Pythagorean theorem, this side would end up, whenever you reduced it, being 6 radical 2. All right, 30, 60, 90. What we try to do is we always try to keep the shortest side equal to the individual variable because it makes the calculations easier. So we take the shortest side and we're going to make that side in. And we could really do that with any of the sides, but it makes it easiest if you use the shortest side. So what happens is the hypotenuse is double that. And this side is n square root of 3. And again, those relationships hold true for any size. So if this side was 5, this side would be 10, and this side would be 5 radical 3. Now, the main reason we're going to use that tomorrow to create our, not tomorrow, but next week, to create our unit circle and that kind of stuff. But the reason why this is important is because this shows that with trigonometry, it doesn't matter the size of the triangle. The angle, with trig is ratios. So no matter how big the triangle is, for that angle, the ratio is going to be the same. So if I take sine of 60 degrees, doesn't matter how large this triangle is, because sine of 60 degrees is always opposite over hypotenuse. The size of the triangle has to do with the n value, right? That's how we make the triangle larger or smaller. Well, because of the ratio, the n values cancel out. So no matter what, sine of 60 degrees is always radical 3 over 2. Doesn't matter how large or small the triangle is. Sine of 60 is always that same number. So sine of 2 degrees is always going to be the same number. Sine of 100 degrees is always the same number. Yeah. So that's part of the reason why we introduced the special right triangles, is because it's an easy way to show that trig does not depend on the size of the triangle, because it has to do with ratios. The ratio remains constant. Okay, so you guys have these on your paper. I'm going to switch to another page. You guys can use your papers to do this. So what would sine of 30 degrees be?
One over two. One over 260.
If you use your special right triangle, 30 degrees, opposite side is n, hypotenuse is 2n, the ends don't matter, because the ends depict the size. And remember, size doesn't matter. So, yes, there's a joke in that. We're going to stay away from that.
You are going to stay away from it.
Yes, I'm going to stay away from that. We don't have time to delve into that joke. Okay, so again, looking at the fact that the ends don't matter, what is tangent of 45 degrees? 1. Because tangent of 45 degrees would be n over n. So again, that's more leading into what we're going to do next week. But you're going to have some problems that are going to use that. All right, trig identities, and then we're done. Trig identities, again, these are things that we're going to use these a lot in Unit 5. But the more you get, if you start using them now, it'll help you, because Unit 5 has a lot of stuff you have to memorize. So the more you start using stuff now and start getting some memorization done now, the more it helps you later. I should probably name these. These are your reciprocal identities. See, I just forgot how to spell reciprocal. I totally spelled it wrong. These are your reciprocal identities. Sine of theta is the same thing as the reciprocal of cosecant. So same thing we already talked about. This just puts it in writing. Cosine is the reciprocal of secant. Tangent is the reciprocal of cotangent. And then you can have the same thing, or vice versa. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. Cotangent is reciprocal of tangent. Okay, and this is one that I didn't mention. These are your quotient identities. They actually introduced another set, but I'm not even going to deal with those because we don't use those at all. The quotient identities you might come in handy a little bit. Tangent is equal to your sine value divided by your cosine value. Cotangent is the same thing as cosine, divided by sine. Again, eventually you're going to have to actually memorize these the way that they look, because you're going to have to use them the way that they look. So the sooner you start, dealing with them and using them in actual problems, the easier they are. And kind of give you an idea, if you open the front cover of your book, mine has tape on it, but pretty much everything inside the front cover of your book, this is what you have to memorize for trig. Including this circle. Circle is what we're working on next week. You have to memorize all those numbers inside that circle. No? You have to memorize all the ordered pairs along with all the angles. I'm going to show you an easy way to get them without having to memorize every single number. Yeah, this big.
We should get some complimentary documents class.
I want a
One
taser.
more piece. One more piece.
If it makes it better, I show you ways of the way that these things come about, which make it a little bit easier to. And a lot of formulas are related to each other, which if you know one formula, you can get the other formula. And with the unit circle, if you memorize one quadrant, you can get the other quadrants.